What's up everyone, and thank you for choosing to learn with LAM. Today we're going to be going through a sample calorimetry problem, which will put together what we learned in our calculating heat and molar enthalpy videos. The equations you're going to need today are Q equals mc delta T and delta H naught equals delta H over little n. And we're going to jump right into our sample problem. We'll start off by giving you a balanced equation for a chemical reaction, which will be the system of our problem. That reaction is copper 2 chloride plus 2 sodium hydroxide makes copper 2 hydroxide plus 2 sodium chloride. And the question is, determine the molar enthalpy of sodium hydroxide in the above reaction if the temperature in a calorimeter increases by 3.20 degrees Celsius when 50.0 milliliters of 0.200 molar sodium hydroxide solution is mixed with 50.0 milliliters of excess copper 2 chloride. Now, every calorimetry problem is made up of two major steps, one involving the heat of the water in the calorimeter, which acts as the surroundings, and one involving the molar enthalpy of the reaction itself, which is our system. The order in which you do things depends on the questions and your own preferences, but I typically start with heat. So Q equals mc delta T, and remember that we're looking at water data for this. Now, you might be wondering how we're going to do this considering there's no water in my reaction. But remember that one of the key assumptions of calorimetry calculations is that the solutions that we use are all dilute enough that they possess the qualities of water, specifically density and specific heat capacity. So if I'm looking for mass of water, I'm actually going to look for volume. And I see here that I'm mixing 50.0 milliliters of sodium hydroxide solution with 50.0 milliliters of copper 2 chloride solution. Now, if I'm mixing these two solutions, their volumes are going to add up. So my total volume is going to be 50.0 milliliters plus 50.0 milliliters, which gives me 100.0 milliliters. Again, density of water is maintained, so 1 gram per milliliter, which gives me a mass of 100.0 grams. If you'd like to see the heat part of this problem done in more detail, the link to the calculating heat video is in the description below. From here, we look up specific heat capacity of water. Again, we're treating the sodium hydroxide and copper 2 chloride solutions as if they have the properties of water, so we don't want the specific heat capacity of either of those compounds. And the specific heat capacity of water is 4.184 joules per gram Celsius. As for temperature change, when a question refers to the temperature measured in the calorimeter, we're talking about the water. So we have positive 3.20 degrees Celsius. Now I just cancel out my units and my calculator tells me we've got 1,338.88 joules, which I'll just convert to 1.33888 kilojoules. Now I've got the heat of water, but I'm really interested in the heat of the reaction. So we're going to do a quick conversion here where the heat of water equals negative heat of reaction. Recall that my water is the surroundings and my reaction is the system, which explains the negative relationship here. So my heat of reaction is negative 1.33888 kilojoules. And then I can set my heat of reaction equal to my enthalpy of reaction since we're assuming that pressure and volume remain constant. So my enthalpy of reaction is also negative 1.33888 kilojoules. Now, I know that some people teach this relationship as simply QW equals negative delta HR, which is true considering our assumptions, but I like to keep them separate to emphasize first the negative relationship between surroundings and system, and then secondly, the assumption of constant pressure and volume, which will not always be the case in higher levels of chemistry. Anyway, from here I have enthalpy of reaction, but I'm looking for the molar enthalpy, so I need my molar enthalpy equation. If you need some clarification on the difference between enthalpy and molar enthalpy, the molar enthalpy tutorial link is in the description below. Now, anytime we're looking for molar enthalpy, we do need to specify what particle in our reaction we're doing the molar enthalpy for. In a calorimetry problem, that's always going to be the limiting reactant. Now, our question actually tells you what the limiting reactant is twice. First, in that it's asking for the molar enthalpy of sodium hydroxide, and then again when it tells you that you've got excess copper 2 chloride. So when we try to find moles, we'll be using the sodium hydroxide information. So this time when we look at volume, we're only looking at volume of sodium hydroxide, which is 50.0 milliliters, and we'll actually be keeping it as volume. So let's convert it to liters for our mole work, which is 0.0500 liters. Concentration of sodium hydroxide is 0.200 moles per liter. So moles of sodium hydroxide is going to be concentration times volume, which is 0.200 moles per liter times 0.0500 liters. Cancel out the units, and that gives me 0.0100 moles. And now back to my molar enthalpy equation. Enthalpy we determined to be negative 1.33888 kilojoules when I'm reacting only 0.0100 moles of sodium hydroxide. But when I divide those two values, I can see that the reaction actually releases 134 kilojoules per mole of sodium hydroxide. And that's that. As always, if you have any questions or if you have any topics that you'd like me to cover, just leave them in the comments below. Good job, everyone. If you find that you need a little extra help, please feel free to check out my other videos for tips and tricks on how to succeed in school. And as always, thanks for learning with LAM.